Hello all, I am Dr.P.PRIYA from S.A.E. Engineering College belonging to the Department of Civil Engineering, and this is a GATE video session on the topic Simple Bending Theory, Fundamentals and Application. Let me get into the topic. Before that, we know that the GATE exam scheduled for 2026 is going to commence on the date of February 7th, 8th, 14th and 15th, and many of you would have registered for the exams, and this is the syllabus for structural engineering, in which I am going to cover the topic of solid mechanics, and under that it is just a simple bending theory is a topic which I am going to concentrate. So to brief about, I am giving an introduction about what is the simple bending theory, and this fundamental of simple bending theory is used in case of beams which is under varying loading conditions. The core concepts such as neutral axis, bending stress distribution and the bending equation is covered in the presentation, and also the assumptions related to simple bending theory is also highlighted. The applications of simple bending theory in case of a standard beam with varying loading conditions which are commonly used in the GATE exams are also covered, and also I have highlighted various problems which were asked in the GATE exams. So going into the fundamentals of simple bending theory, you can see a normal beam. We have a neutral axis, which is an axis, a simple line which transmits the fiber into two different categories. So this simple bending involves a beam which is subjected to moment on both the directions, and with this moment tends the beam to bend, and you have a neutral axis where there is no longitudinal stress, and there is no other stresses involved in this particular axis. This concept is very much necessary to understand the simple bending theory. This one is the key assumptions. The assumptions what we follow in case of a simple bending theory. The first assumption is the beam is initially straight. The second one is the material is homogeneous and isotropic. And the third one is the plane section remains plane after bending. The stresses are linearly distributed. So you can see the maximum stress at the top, and you can see the member is homogeneous and isotropic, and plane section remains plane after bending. This is a bending equation which is m by I is equal to sigma by y, which is equal to E by R, and m represents moment of resistance, I is the moment of inertia of the section about the neutral axis, E is the Young's modulus, radius of curvature is represented as R, sigma is nothing but the bending stress, and y is the distance from the neutral axis. So here when we need this to calculate the stress sigma, we can just bring the other terms to the side, and sigma will be equal to m by I into y. That is how we apply this one. So that it is again repeated here. The section modulus calculation is explained, where the bending stress sigma is equal to m by I into y, and I by y is nothing but the section modulus, and maximum bending stress occurs at the extreme fiber in the neutral axis, which is given by m is equal to sigma into z, and z is calculated by the formula z is equal to I by y. So now we will be seeing about various sections and how we are going to calculate the moment of inertia of various section and how we are arriving at the section modulus. So this is a simple rectangular section where we have a neutral axis exactly at the center with a dimension of breadth as b and depth as d. Generally we know the moment of inertia of this section above the neutral axis, I is equal to bd cube by 12, and distance of extreme fiber from the neutral axis, y max is nothing but the total depth divided by 2, and the section modulus z is equal to I by y, and we get a final value of bd square by 6. Similarly, I am just projecting it for a hollow rectangular section where we have two dimensions of depth and two dimensions of depth and breadth. So here the moment of inertia is given by the formula 1 by 12 bd cube minus small bd cube, and here in similar pattern when we arrive at a section modulus of capital B d cube minus small b d cube by 6 times d. And this is for a circular section, and we have a diameter of d and a neutral axis exactly passing at the center. The moment of inertia of this circular section is given by pi d power 4 by 64, and the distance of extreme fiber is given by y max is d by 2. The section modulus hence calculated comes to around pi d cube by 32 is the formula. So coming into the topic of cantilever beam carrying a concentrated load at the free end, the bending moment of the section is given by nothing but moment is given by load into distance x. So the section modulus Z is calculated as BD square by 6, and the bending stress sigma is equal to the moment divided by the section modulus. So this is again, this is simplified and written as 6Wx by Bd square. The 6 goes to the top, and we arrive at this formula to calculate the bending stress. So you can see the figure here which shows a cantilever beam, and it is applied by a load W at the extreme end, and we are drawing a section X at a distance of X from the load. And then we are calculating the values. When the D value is constant, the width of the section is given by about section XX is given by Bx is nothing but 6Wx by sigma d square, which we saw in the previous slide. 6Wx, the similar one is represented there. When it is calculated for a distance of x is equal to L, that is for the entire span, then we change this x to be L, and this is 6WL by sigma d square. The next one is the calculation when the breadth of the beam is constant. The depth is given by root of 6Wx by B into sigma. We are substituting x is equal to L and arriving at a depth value. So this is for a cantilever beam carrying a uniformly distributed load. So this is, the previous case was a concentrated load problem, and now it is for a cantilever with UDL. So we know that in the UDL the load will be concentrated exactly at the center. So here the bending moment is given by W x square by 2. So this x is the length, and section modulus BD square by 6. And the maximum bending stress, when we substitute the value of M and Z, we arrive at a value of 3Wx square by BD square, which we are going to apply for the problems. So similarly, like the previous case, we are arriving at a portion where D is constant, and then when the value of B is constant, and we are getting at two different formulas for B and D. So this is for a simply supported case with point load at the midspan. We are calculating the value. So this is the moment formula, that is bending moment at the section, which is given by the load divided by 2 into x, which is exactly at the center. So we have calculated it as 1 by 2, section modulus BD square by 6, and we arrive at the bending stress of M by Z as 3Wx by BD square. So when the depth is constant, the width of the section is given by, we are substituting the value as 3Wx by sigma d square, and this is how we arrive. The load is acting at the center. We are giving a section, cross section XX at a distance of x from the left support A, and then when the load is constant, that is constant D, we have this kind of variation. So this is a case of simply supported beam with UDL. So in this case, we have the moment as WL by 2 into x minus Wx square by 2. So first one is the load is uniformly distributed, and it will be concentrated exactly at the center. And so we are simply substituting this and calculating the moment bending stress for this particular case. So now we will see some of the problems which has been asked in the GATE examinations. So the first problem what we are going to discuss is the maximum bending stress induced in a steel wire of modulus of elasticity 200 kilonewton per mm square and diameter 1 mm when wound on a drum of diameter 1 meter is approximately equal to, and they have given four options: 50 Newton per mm square, 100 Newton, 200 Newton per mm square and 400 Newton per mm square. So here they have given the terms such as modulus of elasticity is given, diameter of wire is 1 mm, diameter of the drum which wire is wounded is 1 mm. Radius, we are converting the radius from the diameter and taking it to be by 2. Diameter by 2, it is 0.5 mm. So similarly, we draw an approximate drawing which shows a circle where the steel wire is wound, which is 1 mm here. So the bending equation what we are going to use here is m by I is equal to sigma by y is equal to E by R. So here they have asked you to calculate the maximum bending stress. So we apply sigma is equal to E by y, E by R into y. We are just considering only this set of equations, and we are substituting the E value which is given in the question, and the R value is also given. So we substitute and get the value to be 200 Newton per mm square. So our option C is the correct answer, 200 Newton per mm square. So second question is, the basic assumptions of plane section normal to the neutral axis before bending remains plane and normal to the neutral axis after bending leads to. This was one of the question asked. So the answer for this one is option C, that is linearly varying strain over the cross section. That is the basic assumption, plane section normal to the neutral axis before bending remains plane and normal to the neutral axis after bending leads to linear varying strain over the cross section. So option C is the correct answer. So the next one is a problem wherein a simply supported beam of uniform rectangular cross section of width B and depth h is subjected to a linear temperature gradient of 0 degrees at the top and T degrees at the bottom as shown in the figure. The coefficient of linear expansion of the beam material is alpha. The resultant vertical deflection at the midspan of the beam. They have asked you to calculate the resulting vertical deflection at the midspan, and they have given you few options. They have represented the beam which is of L length, and the temperature variation at the bottom is T degrees and at the top is 0 degree. So we are going to calculate the value. So average change in temperature is T by 2. The compression at the top of the fiber is given by the formula L into alpha into T by 2, and the elongation temperature strain is calculated, and then we are substituting it using the bending equation m by I sigma by y is equal to E by R. So when we substitute the strain divided by y, which is equal to 2 E naught by h, we simplify and arrive at a formula of alpha T L square by 8h. So this is the option, that is your option D, alpha T L square by 8h. Option D is the correct answer. And the last problem is, a homogeneous simply supported prismatic beam of width B, depth D and span L is subjected to a concentrated load of magnitude P. The load can be placed anywhere along the span of the beam. The maximum flexural strength developed in the beam is. So we are supposed to find the maximum flexural strength. So the diagram represents a small simply supported beam with load P, and you can see the cross section with breadth B and depth D. So the maximum bending moment developed at the midspan of the section with a concentrated load P is given by M is equal to PL by 4. This is the formula, maximum bending moment formula, and the I value is given by BDQ by 12, and the distance of fiber from the neutral axis is given by D by 2. So the maximum flexural stress which is asked in the question can be calculated by sigma max is equal to m by I minus y. So we know what is the value of m, we know I. Simplifying, we get the value to be 3PL by 2BD square. So which is option D, 3 by 2 PL by BD square. So that is the formula that we arrive, and that is the answer. So thank you so much. We see you in the next lecture.